Hello and welcome everyone. Thanks for watching this video presentation about our recent work here in Institute of Information Technology in Klagenfurt University. We proposed this paper to ACM MMC's 2020 conference, which was planned to be held in Istanbul, but due to COVID-19 pandemic, the plan changed and as you should know is happening in form of an online conference. CAdViSE is a cloud-based adaptive video streaming evaluation framework for automated testing of media players. My name is Babak and I'm going to walk you through this presentation today. First, we are going to briefly review the motivations behind this project. After that, we will discuss the architecture of the testbed in more details. And finally, we would have a look at some experiments and results. But first, let's see why such a framework would be a handy tool set for real-life software development and even research and academic projects. There are lots of different ABR algorithms and also various implementations for each algorithm that can be taken into consideration when developing a media player for adaptive video streaming. Our testbed can be used to evaluate various metrics and provide insightful statistical results of how a media player can actually adapt the stream to ups and downs of a network. As a matter of fact, a network connection has different shapes during each session, and the latency, available bandwidth, packet loss, even packet corruptions could happen after initializing a network connection. CAdViSE helps to mimic the real-life connections quality and provide the environment which very much close to what's happening in our daily routines of using internet connections. Proposing this automated test framework, we always had in mind the continuous integration and development, which is a norm in quality assurance perspective of the software construction. Therefore, we designed a framework, CAdViSE, in a way that is easily integratable with CI/CD pipelines. In the next slide, we would describe and talk more about this aspect of the testbed. But next is the visualizing the statistical report in form of diagrams. This could help the development teams to better understand the improvable points and compare multiple media players in a glance. So this was important when we were proposing this framework. Last but not least, we wanted to provide a framework which is easy to deploy and maintain in a modern environment, and that's why we used cloud infrastructure instead of individual computers to run the test. So in this framework, we are not using bare metal machines, but we are using cloud infrastructure, which is much more easier to deploy the test, and also it's integratable with normal development pipelines. It would work like a normal unit testing of the developed source code, and is much more easier to be maintained comparing to the to having physical machines running the tests. Moving on from the project motivations and of course the introduction, I would like to introduce to you the architecture of the framework. There are three main components or modules in this system, which makes the framework more flexible in terms of routine upgrades or adding new features or updating the softwares. First is the application. Application component consists of shell scripts basically, which gets executed in different points of time during running the test. There are three types of scripts: runner script, initializers, and starters. In order to initiate the framework itself, we have developed a script called runner script. That is the entry point to executing experiments, providing a set of attributes such as necessary parameters for cloud management, and of course experiment specific parameters like number of experiments we want to run, or names of players that we want to test, etc., etc., and then running the runner script would spin up EC2 instances in AWS cloud. These instances are normally ready to be used in only few seconds with a predefined operating systems. Depends on the need of the client, of course. But for this framework, we are using Amazon Linux machine images that gets run on each EC2 machine and being managed by the SSM. Once we have the EC2 machines up and running, the application would wait for network interfaces to have a publicly accessible IP address assigned to them. This usually takes few other seconds, and the application would be on hold, would sleep on this moment until the IP address is accessible. And then next we inject two other tiny scripts plus a small configuration file into each EC2 instance. The other two tiny scripts are initializer script and starter script. The initializer script will install the required libraries and Linux packages in order to make the machines ready to start the job. For example, one of the softwares that gets installed in this step is the Docker software itself. And also we would need the images, the Docker images that would be fetched from the Docker hub and stored in each EC2 instances until we execute the starter script, and those Docker images would be run inside the Docker containers. When all the EC2 instances are initialized and are in ready state, the last script will be invoked and will cause the experiments to be started, by which means the players actually start playing the provided content. Meanwhile, the runner script will keep on monitoring the statuses after each step and make sure that there is no failure or error. Otherwise, it will continue the experiment, and once the duration of the defined experiment is finished, the EC2 instances will be terminated by this runner script again. The second component is the cloud infrastructure itself. This component includes the Docker containers with pre-installed software such as VNC server or Selenium test software. We use VNC to monitor the running test in real time, and this is only possible if the runner script has been executed in debug mode. So if we run the test in production mode, the VNC server wouldn't be installed and there will be another Docker image being pulled for the tests, and that is considered the production mode, and then we don't have the VNC server, therefore we cannot really monitor the test in the real time. The Selenium is used to control the players in a web browser. Basically, it would execute the players in form of HTML files in a web browser, and it would start playing the players by sending it some commands. To emulate the network shape, we are using another Docker container which is based on Docker traffic control. This container allows us to change the network attributes in different points of time and shape the network that was defined by runner script parameters. These parameters would be passed to the runner script by a JSON file, and inside that JSON file we can easily define the available bandwidth for each point of time in the experiment. EC2 instances, which are virtual machines from AWS, are used in this framework to control and also monitor the instances. We are using AWS SSM Systems Manager agent from AWS itself. The players are also the content. The players and also the content which will be played during the test are stored in AWS S3 buckets. And finally, we use CloudWatch in order to get some statistics about the running machines, for example, the amount of memory that we are using or the number of CPU cores that is being used by the test, and etc. Next is the analytics component. When we run the test, it would cause the players which are equipped with Bitmovin analytics plugin to fetch a specific video segments and actually play the content. these segments would be chosen by the player algorithms based on the network that we have provided for each player. And then the Bitmovin Analytics plugin would then collect useful information from each session and send it back to the servers, to the Bitmovin servers. A lot of metrics in the next slide we will go through, and we will see what are the possibilities with this plugin and also the dashboard. Having those information, we can see lots of different diagrams and reports in Bitmovin Analytics dashboard. Again, in next slide we would see that, and these two software would be considered the analytics component of the testbed itself. In order to demonstrate our testbed, CAdViSE, we have arranged a simulation in which 5 experiments being executed. Each experiment would take 9 minutes to finish, and it means that the whole demonstration would take 45 minutes in total. We have used T2 medium-sized EC2 instances which have 4 GB of memory and 2 CPU cores. We have tested 3 major media players, Bitmovin player, Shaka player, and Dash.js player for this test. The network shape is defined in 3 points of time. In the beginning we had 4 megabits per second of available bandwidth, and after 3 minutes we changed this, we decreased to 800 kilobits per second, and again after 3 minutes we increased back to 4 megabits again. On the right side you can see 2 diagrams which was generated by AWS CloudWatch. One for network packets ingress, and the other one is the CPU usage percentage. And as you can see in this figure, each player is indicated with a different color, and the values in each point of the time can be compared among all 3 media players. In this slide, as you can see, a small part of the Bitmovin Analytics dashboard is shown. There are important metrics presented here, for example the startup times, average bitrate, or even the number of failures or errors that happen during the streaming session. Again, comparing the media players is obviously very easy and feasible. Using these metrics, development teams can have good understanding of what are the weaknesses of each media player and have room to be improved. As I said, this is only a small part of what Bitmovin Analytics is providing, and there are a lot of other useful diagrams that can be simply customized for each experiment in CAdViSE framework. I would like to appreciate my team support here in Athena Lab for this project, and also Bitmovin engineering team, which provided us with good help and support. Also, thanks to you for watching this presentation. If you have any questions, feel free to reach out to me or my colleagues. Stay healthy and have a good time ahead.